Our next team is 16236 Juice. They're presenting online from Folsom, California, and they'll be talking about introduction to robot consistency. Juice is a student-led FTC team founded in 2019 and has grown to 15 members in grades 8 to 12, organized into outreach, hardware, and software subteams. Juice is dedicated to and united by the shared mission of promoting STEM in the local community. Everyone, please welcome 16236 Juice.
Hi everyone, we are Team 16236 Juice, a student-led FTC team in Folsom, California. Founded in 2019, our team consisted of 9 high school students. Now we currently have 15 students ranging from the grades 8 to 12th grade. We compose our team into 3 different sub-teams: outreach, hardware, and software. Although each sub-team works on different tasks, we operate as one toward a greater purpose. Here in Team Juice, we are dedicated to spreading the values of STEM in our local community.
Try to make sure that we can score like a relatively like average high amount of points rather than having some really high or really low amount of point scoring within one tournament. This is like especially noticeable in earlier tournaments, in early qualifying tournaments, where like there are less like super strong robots. And so if you have if you have one bad game, it's really likely that you may lose out on a alliance captain position, and then you're less likely to qualify to regionals or worlds or any future events. So for example, in Into the Deep, we prioritize making sure that we can score each spike on the field rather than going for a submersible intake. So we could have possibly sped up our intake, rushing it, trying to get a 6th sample for the high basket, but we just didn't find it to be worthwhile to aim for that while we could just prioritize consistency and make sure that we make it to those higher events in the first place. All right. So our second key idea is pretty similar to the first one. We want to prioritize reliability of our robot. So we just want to make sure that everything will always work and always work when we want it to. So for example, our robot this year, we just had one intake and outtake. We didn't have like any transfer system. So in the picture, you can see we just extend our entire horizontal extension upwards to score, whether it be in the high baskets or on the high chamber, whatever. And not having this transfer, it just allows it so that there's one less thing that's less likely to break. So just because you have to go up anyways, right? So if you're going up and then your transfer breaks, if just that transfer breaks, you can't score any more points. And we just want to make sure that we get everything possible just so that we can score every last point like reliably. And then a second part of this is about our odometry. We initially had a variety of different sensors. We had the pinpoint, we had the like dead wheels, we had a limelight on our bot initially, and you can kind of see these 3 like visuals on a picture of FCC Dash here in picture number 1 and 2. You can see that they're not like agreeing with each other too well, but we ended up doing is we ended up just making sure that one of them worked well enough on its own, and it would just prevent that anything we do with combining, say, one odometry to another, prevent any issues between that and like drastically affecting our auto. And so with the previously mentioned limelight, we had considered that we want to do submersible intake just because in auto it's more points, right? But we got rid of this idea. We found that our robot like tended to not be fast enough for this. We like tried to make updates for it, and then additionally, it was hard to make sure to that for any like submersible like orientation, because of like the great variety of randomization and our active intake, that it's harder to make sure we get the sample that we want. All right. And then our third idea will be testing. And we just want to make sure that for all possible cases, if something like ever happens, that it would still work. Like we don't want any like one small error to break anything. So what we do is, just because like it works for like a general case, like say if we run a test match and it's just or a solo match, and everything works fine, we want to make sure that if you for some reason are in a scenario where something doesn't happen the way you expect it to, that would still work. So you want to make sure that you're not testing for the general case, but you're testing for the worst possible scenarios. And you want to make sure that you know that if problems occur, you want to know which subsystems are at fault for this. And so then you just go bit by bit. You just want to test every small portion that you can, and then just test over and over again. We want to make sure that just because so that we can say yes, we tested it, but if we only tested it once, it might have just been a fluke that one time. And so this is a picture of a motion profile we were implementing for our lift, just so it wouldn't like just immediately slam down. We had like a pretty weird issue with that. And so you can see here we have like a weird jump up here. So we were unsure where to go. So we didn't want to keep testing this on the robot itself because we don't want to risk any like damage. And so we actually simulate it in MATLAB first to make sure that once it's theoretically supposed to work, it will work. And then after that, we can start testing for any edge cases that we might find, say, like going from one lift height to another and then immediately to another. All right, so that'll conclude our presentation, and I'll let Sanjali handle the questions.
Are there any questions for us?
We have an online question from Jeff. He asks, why do you not use a Kalman, and because your sensors seem to not be entirely accurate?
Yeah, so our pictures, it's slightly weird. So the our dead wheels, can we go back to one of the slides with the yeah, this way. So we can see so you can see that there's like 3 different odometries. We have the what is it, Otos on the red circle, and we have Limelight on the green, and then the Go Build the Dead Wheels on the yellow. And so the problem is not that our sensors aren't entirely accurate. It's just that we have the Go Build the Dead Wheels were very accurate. It's just that everything else we try to combine it with to make sure to try and say like if they fail, what would happen. Everything we tried to add to like prevent that was actually just further from where it was actually the robot actually was. So we try to implement a Kalman filter to like combine these values. It's just that combining them ended up giving us a less accurate result than just using the dead wheels.
Do we have any more questions?
Are there any questions in person? Okay, I think that's it. Thank you.